In today's lecture, the final lecture of the course, we've carried on looking at our brief summary of particle physics. I started off by going through what I was discussing with you about strangeness in the last session. So we've seen that just as particles have properties like spin and mass, so we can assign another property for particles which are involved where the strong force is involved, which are the hadrons. We see that strangeness is important. We can see that if we then go out and we plot particles, we arrange particles on a sort of XY-ish kind of plot, where for instance we plot the strangeness versus the charge, and we plot the charge on sloping axes, we see this rather beautiful symmetry of particles beginning to come into play in something called the eightfold way. Now, the eightfold way is a way of arranging particles, and it's allowed people in the history of particle physics to actually predict where new particles are going to come from, what their properties are going to be. So for example, you could predict for the spin 3/2 baryon the existence of the omega minus particle, and Murray-Gell-Mann did this and told particle physicists where to go looking for it and also what its properties were going to be, and he was proved correct. So we have this beautiful symmetry in particle physics that begins to allow us to express a lot of ideas, and is really a very powerful technique in developing physics. So to try and understand this symmetry, Murray-Gell-Mann came up with the quark theory of matter. He postulated that in fact particles like protons and neutrons were made up of even smaller particles called quarks, and there were 3 quarks in each proton and neutron. He said that the interesting thing about quarks was that they had fractional charge and they had fractional baryon number. And by using this, he could explain all the properties that were observed in the eightfold way symmetries. So for instance, if you go and look at the proton, we see the proton's made from 2 up quarks and a down quark. If you add up the fractional charges and the fractional baryon numbers, you'll come up with exactly +1 for the charge and +1 for the baryon number. If you then look at the spin, now remember quarks have half-integer spin, they're fermions, we can see that we get the same answer of +1/2 as we'd expect. The reason for that, although we have the 3 quarks, we have 2 up quarks and a down quark. The up quark has spin 1/2. Because of the Pauli exclusion principle, the other up quark must have a spin of -1/2, because we can't have all these particles in the same quantum state. The down quark has spin of 1/2, which gives a total spin of 1/2 for the proton, exactly as we expect. The neutron, by contrast, is made from an up quark and 2 down quarks, and we can see if you follow everything through, we get a charge of 0, we get a baryon number of 1, we get a spin of 1/2, we get a strangeness of 0, exactly as we expect. So now we can look at beta decay in a new way by looking at the quark theory of matter. And we can see that what happens in beta decay is an up quark must convert into in beta decay we have a neutron going to a proton, so a down quark must convert into an up quark, okay, in beta minus, emitting an electron and an electron antineutrino. We can also see the mesons. If you go and look at the mesons, okay, another class of matter, remember, we can see that these are made of a quark and an anti-quark pair, so mesons are made in pairs. Look at for instance, the sigma plus is made for an up anti-down. You follow everything through. If you then consider the mass of the proton or neutron, if you consider it as being simply the sum of the masses of the quarks, and that's a very naive point of view, what you have to do is you have to consider the potential energy of the quarks, the kinetic energy of the quarks, and all of these are manifested in the mass. So we can see that the sum of the mass of the quarks, for instance in a proton, is only about 20 MeV/c², whereas the actual mass of a proton is 938 MeV/c². So these energy contributions are enormous when we come to these fundamental particles. In order to finish the standard model of particle physics, I looked briefly at forces. We saw again the strong, the weak, gravitational and electromagnetic forces, and we came up with the idea of charge-carrying particles, which are the way the force is felt. So for instance, the electromagnetic force, we have the photon. Gravitational force, we have the graviton, which hasn't yet been detected. Then we have the W and Z bosons for the weak force, and a particle called the gluon for the strong force. Hay fever doesn't help when you're doing these lecture summaries. We saw that particle physics was really important because the energies that people are getting in the particle accelerators takes us right back to the kinds of energies we had at the dawn of the universe. And by understanding particle physics and how particle physics works, it tells us a great deal about the start of the universe. It tells us about what happened in the Big Bang. How did matter generate after the Big Bang? Why is there an asymmetry between matter and antimatter, where we observe far more matter than antimatter? All of these questions are fundamental questions, and until we understand particle physics, we won't understand the answer to these questions. So in understanding particle physics, we find out about where we come from, and ultimately by understanding about where we come from, we find out the ultimate fate of the universe, where we're all going to. So these really are the fundamental driving questions of mankind, and we've seen throughout the course on properties of matter that the properties of matter have given us an understanding of the properties of matter, have given us a full insight into the universe around us, led us to more questions, more exciting questions, more interesting questions. Being able to predict how matter behaves really is one of the key tools of the physicist, and it's a subject where there's still plenty of mileage to go. So once you go out there and start doing this, you'll see that there's plenty of room to make contributions in this area. It's been one of mankind's great questions. So I hope you enjoyed the course. That's the end of the course. I finished just briefly with a few pointers about the exam. The key point is, remember not to take graphical calculators or programmable calculators into the exam hall, because the invigilators are perfectly in their rights to take them away from you.